Good day, everyone. Welcome to ME725 Foundations of Optimization. Today, we'll be talking about the relative minimums and maximums. In this particular section, now we will be extending one of the more important ideas from calculus into functions of two variables. So we are going to start looking at trying to find the maximums and the minimums of the functions. In this particular lesson, also, we will be going to be looking at identifying the relative minimums and relative maximums. So let us recall as well that we will often use the word extrema to refer to both maximums and minimums. So what is our intended learning outcomes for this particular lesson? So here, our intended learning outcome, so we are expected to define relative minimum and maximum for functions of two variables. And also, we have to define critical points of functions of two variables. And lastly, we are going to find and classify all the critical points of the functions with two variables. So let me start with the definition of the relative minimum and maximum. So what is then the relative minimum and maximum? So the definition of relative extrema for functions of two variables is simply identical to that for functions of one variable. We just need to remember now that we are working with functions of two variables. So for the sake of completeness, here is the definition of the relative minimums and relative maximums for functions of two variables. Note that this definition does not say that a relative minimum is the smallest value that a function will ever take. It only says that in some region around the point AB, the function will always be larger than the function of f of AB. Outside of that region, it is completely possible for the function to be smaller. Likewise, a relative maximum only says that around the point AB, the function will always be smaller than the function f of AB. Again, outside of the region, it is completely possible that the function will be larger. So next, we need also to extend the idea of critical points, especially for the functions of two variables. So let us recall that a critical point of the function f of x was actually the number of the number x that is equivalent to c, so that either the derivative of the function c is equal to 0 or the derivative of the function c does not exist. So we have a similar definition for critical points of functions of two variables. So in fact, no, we will use this definition of critical point more than the gradient definition, since it will be easier to find the critical points if we start with the partial derivative definition. Note as well that both of the first order partial derivatives must be 0 at point AB, and if only one of the first order partial derivatives are 0 at a point, then the point will not be a critical point. So we now have the following fact that at least partially relates critical points to relative extrema. It is stated that if the point AB is a relative extrema of the function, the function of f x of xy, and the first order derivatives of the function f of xy exist at a certain point AB, then AB is also the critical point of the function of f of xy. Take note also that this does not say that all critical points are relative extrema. It only says that the relative extrema will be the critical points of the function. To see this, now we can also consider the function of f of xy, which is equivalent to the product xy. The two first order partial derivatives are the uh, first order partial derivative of function f with respect to x is equal to y, and the first order partial derivatives of x with respect to y is x. So the only point that will make both of these derivatives zero at the same time is 0 and 0. And so 0, 0 is called the critical point for the function. However, now there is no way that 0, 0 can be relative extrema, since these critical points exhibit a kind of behavior which we call the saddle points. We have to be careful to not misinterpret the results of this fact. It is very useful in helping us to identify relative extrema. Because of this fact, we know that if we have all critical points of a function, then we also have every possible relative extrema for the function. The fact tells us that all relative extrema must be critical points, so we know that if the function does have relative extrema, then they must be in the collection of all the critical points. Remember, however, that it will be completely possible that at least one of the critical points won't be a relative extrema. So once we have all the critical points in hand, all we will need to do is test these points to see if they are relative extrema or not. To determine if a critical point is a relative extrema, and in fact to determine if it is a minimum or a maximum, we can use also this fact. So suppose that AB is a critical point of the function f of xy, and that the second order partial derivatives are continuous in some region that contains the critical point AB, then D is equivalent to the second order partial derivative of x with f with respect to x times the second partial derivative of f with respect to y minus the square of the mixed second order partial derivative of xy, considering the critical points. So we then have the following classifications of the critical point. So if d is greater than 0 and the second order partial derivative of x with respect to x is greater than 0, then there is a relative minimum at the critical point AB. Second, if d is greater than 0 and the second order partial derivative of f with respect to x is less than 0, then there is a relative maximum at point AB. Third, if d is less than 0, then the point AB is what we call the saddle point. And the last one is if d is equivalent to 0, then the point AB may be relative minimum, relative maximum, or a saddle point. Other techniques would need to be used to classify the critical point. Let us see a couple of examples. First, we are going to find and classify all the critical points of the function f of xy, which is equivalent to 4 plus x cubed plus y cubed minus 3xy. Now, the way that we are going to find the local minimum and maximum is simply by using the second derivative test. And in order to use the second derivative test, we are going to need all the three second order partial derivatives of the function f of xy. In order to get the second order partial derivatives, of course, we need to find our first order partial derivatives, so that this is going to be our first step. So finding the first order partial derivatives, uh, we are going to say that the partial derivative of f with respect to x is going to be equivalent to 3x squared minus 3y. And the first order partial derivative of function f with respect to y is 3y squared minus 3x. Now for the function, for the first order partial derivative of f with respect to y, we consider that x will be considered as a constant. So that is why we have uh, 3 x will be constant. So 3x. So instead of saying negative 3xy, so the partial derivative for that with respect to y is negative 3x. And of course, after getting the first order partial derivatives for the function f with respect to x and y, we also have to find the second order partial derivative of f with respect to x. So from here, from our 3x squared minus 3y, so we have 3 times 2, that's 6, so 6x. And of course, for negative 3y, that means 0. Next, for the second order partial derivative of f with respect to y, so here we have 3 times 2, that's 6, 6y, and of course, negative 3x is 0. So we have, finally, the second order partial derivative of f with respect to y is equal to 6y. And the third one is the mixed second order partial derivative xy, which is, we can refer this to our um, first order partial derivative of f with respect to x, and then we consider next with respect to y. So with respect to y, then this can be considered as constant here, and then we have negative 3, which is actually the coefficient of y. So then we have now all the three second order partial derivatives of our function f of xy. So next is, we will now be finding the critical points. Now using this three second order partial derivatives of the function. So critical points will be somehow the solutions to the system of the equation. So what particular equations then? So these are the two. We have the first order partial derivatives that will be equated both to 0. So we have 3x squared minus 3y is equal to 0, and also 3y squared minus 3x is equal to 0. Now, this is a nonlinear system of equation, and this can, on occasion, be difficult to solve. However, in this case, it's not too bad. We can solve the first equation for y as follows. Next, so we have here now 3x squared minus 3y is equal to 0. Then we can have um, we can divide, or we can add both sides first by 3y. So making this as 3x squared is equal to 3y. Or by using the property of symmetry, and then by dividing both sides by 3, we can actually arrive at an equation y is equal to x squared. Plugging this into our second equation gives, we have here, we substituted our y by x squared. So we come up with 3x to the fourth power minus 3x. And this can be factored as 3x times the quantity x cubed minus 1 is equal to 0. So from this, we can see that we must have x is equal to 0 or x is equal to 1. Now we can use the fact that y is equal to x squared. So to get the critical points now, so we have here when x is equal to 0, then we are to replace 0 to our first equation here. Y is equal to x squared, so x will be replaced to 0, so therefore our y is 0. So our first critical point here is 0, 0. Second, when our x is equivalent to 1, then we will replace x by 1. So this becomes y is equal to 1 squared, and that is equivalent to 1. So therefore, our second critical point here is 1 and 1. So we get two critical points. So we have 0, 0 and 1, 1. And of course, we have also to recall our three second order partial derivatives, which are 6x, 6y, and negative 3, respectively. So what are we going to do then? All we need to do now is to classify them. So to do this, we will need D. Now, D is actually defined as the product of the second order partial derivative of x with respect to f, derivative of f with respect to x, times the second order partial derivative of f with respect to y, minus the square of the mixed second order partial derivatives xy. Okay. So what are we going to do now is to simply replace. So we have the 6x times 6y minus the square of the quantity negative 3. Then we are going to simplify this. So that means we have 36xy minus 9. So to classify the critical points, all that we need to do is to plug in the critical points and use the fact above, or we have to use the fact that was presented earlier to classify this critical points. So let's start first with 0, 0. For 0, 0, we have our D for 0, 0. So we have to replace x and y by 0. So 36 times 0 is 0. And 0 minus 9 is actually negative 9, which means that negative 9 is actually less than 0. And so if for 0, 0, D is negative, and so it must be a saddle point. And then let's have the second critical point. Have 1 and 1. So D here for 1 and 1 is equivalent to 36 times 1 times 1 is 36, minus 9 is equivalent to 27, which is greater than 0. And since where D is greater than 0, so we need to evaluate the second order partial derivative of f with respect to x using our critical point 1 and 1. So, and that is 6 times 1 is equivalent to 6. And since our second order partial derivative of f with respect to x is positive, which is greater than 0, so we must have a relative minimum. For the sake of completeness, so here is the graph of this function. So you can see there is a saddle point and we have the minimum, relative minimum. Okay, so let us have now another example. Let us find and classify all critical points of the function f of xy, which is equivalent to 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2. So for our solution, Again, we will do the same thing as what we did in our first example. So our first order partial derivative of f with respect to x is equivalent to 6xy minus 6x. So here we have with respect to x, so we have 3x y, and this y cube is actually constant, that means 0. And then we have also um, 3x squared, so that becomes negative 6x. And of course, these two are considered as constants, so therefore they are both zeros. And then for the first order partial derivative of f with respect to x is 3x squared plus 3y squared minus 6y. So if we are going to consider here, so we have 3x squared, okay, and then we have, because since this is considered as a constant, and for y cubed this is 3y squared, and of course this is 0 because this is considered as constant. And then for negative 3y squared, the derivative is negative 6y. And of course, for 2, that is constant, so that means 0. Then let's proceed to the second order partial derivatives of f with respect to x, with respect to y, and of course the mixed second order partial derivative xy. So here, for the second order partial derivative of f with respect to x, so we consider this one. So with respect to x, so therefore we have 6y, and we have 6. Now, why 6y? Because y is considered as constant here. Okay, so we have 6y as the coefficient of x, so therefore our derivative here is 6y. And for the second term, we have negative 6x, so that is negative 6. And then let's proceed to the second order partial derivative of f with respect to y. So with respect to y, so here, this is considered as a constant. So that's 0. And then we have here 3y squared, the derivative is 6y. And for negative 6y, that is negative 6. So if you can see, the second order partial derivatives of f with respect not both to x and y are actually the same. Now let's find out what is actually the mixed second order partial derivatives xy. So we have here 6x. So from our first order partial derivative of f with respect to x, so we consider here our here. Now we consider here as y, so we have 6x. No? 6x, since our x here is considered as a constant. So, and then since x is constant, so the second term means the derivative is actually 0. So finally, we have all the three second order partial derivatives. So we can now proceed to finding the critical points. So what we need to do here is to actually solve or to equate first the equations for the first order partial derivatives. So we will equate this to 0. And we have to solve or find the values for x and y. Okay, so here, these equations are a little trickier to solve than the first set. But once you see what to do, they really aren't terribly bad. First, let's notice that we can factor out a 6x from the first equation. So from our first equation, we notice here that the common is 6x. So we have to factor this out. So 6x, then we have to divide the first term 6xy by 6x. So we have y, then negative 6x divided by 6x is equal to negative 1. So, and this is still be equated to 0. So the factors are 6x and y minus 1. So we can see that the first equation will be 0 if our x is 0 or our y is equal to 1. Okay, so take note of that. So this is actually the tricky part here, because if we are to simply eliminate negative 6x by simply adding both sides by 6x, so we will be having 6xy is equal to 6x, in which we can actually just simply divide both sides by 6x, so we can arrive at y is equal to 1. However, now if we just consider that process or that kind of solution, we will not be able to find the other value, or the value for x. So in this case, in this particular example, as factoring, as factoring the terms here, now we notice that there exists an x which is equivalent to 0. So we will be very careful to not just cancel x from both sides. If we had done that, then we could have missed x equivalent to 0. So to find the critical points, we can plug this individually in our second equation and solve for the remaining variable. So let's start first with x is equivalent to 0. So we will plug this in to our second equation. So our second equation is 3x squared plus 3y squared minus 6y is equivalent to 0. So when x is 0, then this becomes 0 here. So what is left is 3y squared minus 6y. And this can be factored out as 3y times y minus 2 is equivalent to 0. So therefore, we expect that our y here has two possible values, and y is 0. The other one is y is equivalent to positive 2. And then let's plug in also the value for our y, which is 1. So in our second equation, so when y is equal to 1, so we have here 3x squared. And then if y is equal to 1, so the square of 1 is 2, the square of 1 is 1, sorry, times 3 is equal to 3. And then 6 times 1 is 6, so that's minus 6 here. So 3 minus 6, that is negative 3. So we have 3x squared minus 3, and we notice that these two are actually common. 3, the common is 3, so we can factor this out. So 3, and then we divide 3x squared by 3, so we have x squared, and of course negative 3 divided by 3 is negative 1. And then if we are to factor out now for x squared minus 1, that's the difference of two squares, so we can have an x which is equivalent to 1 and x is equivalent to negative 1. Okay, so then we have the critical points for this particular example. So again, the critical points here we have when x is equal to 0, we can have 0, 0, and 0, 2, since we have two possible values for y when we plug in x is equal to 0. And then for y is equal to 1, we can have the critical points 1 and 1, and as well as negative 1 and 1. So it is quite different from the first example, since we have four critical points. Previously, we only have two. So now we need to classify these critical points. And to do this, we'll need the general formula for D. Okay, again, our D is simply equivalent to the second order partial derivatives of f with respect to x times the second order partial derivative of f with respect to y minus the square of the mixed second order partial derivative xy. So of course, Now what we need are our three second order partial derivatives. So here it is. So we have 6y minus 6 for the second order partial derivatives of f with respect to x. And then same also with the second order partial derivative of f with respect to y. And lastly, we have 6x for our mixed second order partial derivative xy. We just simply follow the formula for b and then simplify. So we will be able to get the square of the binomial 6y minus 6 minus 36x squared. So we will be using this formula for b and replacing our critical points and trying to check to our reference for the values for our d. Let's start first with 0, 0. Now for 0, 0, with this formula for b, we will replace x by 0 and y by 0. So if this is 0, then we will have negative 6 and squared, that is positive 36, minus the 0 is 36. And take note, 36 is greater than 0. So if it is greater than 0, we need to um, evaluate the second order partial derivative of f with respect to x, and which is actually located the upper right hand. So we will replace y by 0. So 6 times 0 is 0. 0 minus 6 is negative 6. So we have a second order partial derivative of f with respect to x, which is equivalent to negative 6, which means this is less than 0, and consider uh, that this particular point is our relative maximum. And then like we will proceed to second critical point, which is 0, 2. So we will do the same thing. We use the formula for d and replace the values 0 for x and 2 for y. Okay, so if our y is 2, then this becomes 12. 12 minus 6 is 6. 6 squared is 36. Minus, so our x is 0, so that means 0. So 36, again, this is the same as our first critical point. This is again greater than 0. So what we need to do is to evaluate the second order partial derivative of f with respect to x using the value or the point 0, 2. So 0, 2, so our y is 2, so 6 times 2 is 12, minus 6 is positive 6. So this time, this is greater than 0. If it is greater than 0, so it is expected that this point is considered as our relative minimum. And we still have other two critical points, and these are 1 and 1. So again, we have to follow the formula for d, and we will replace x by 1 and y by 1. So 6 minus 6 is 0. So automatically this one is 0. And then for x is 1. So that means we have 0 minus 36, and that is negative 36, which is less than 0. And if it is less than 0, of course, we don't, there's no need for us to compute for or to evaluate for the second order partial derivative of f with respect to x, but we consider this point as our saddle. And then lastly, we have negative 1 and 1. For d, we have to place again the variable x with negative 1 and our variable y with positive 1. So 6 times 1 is 6. 6 minus 6 is 0. So 0 squared is 0. Minus 36. And the square of negative 1 is positive 1. So 0 minus 36 is still negative 36. So which means that this is considered as our saddle point. So there are two um, saddle points here, and then we have the relative minima and the relative minimum rather, and the relative maximum. So to summarize everything, so we have 0, 0 is our relative maximum, 0, 2 is our relative minimum, and both 1, 1 and negative 1, 1 are the saddle points. And here is also the graph of the surface for the sake of completeness. So I hope you learned something today with our lesson for relative minimums and maximums. Our references, we use this one, and I also give thanks to the presentation template that's actually used here. That was created by Slides Go, including icons of flat icon and infographics and images by Frippic. Thank you so much for listening. Bye bye.